Thank you very much. So I was very happy to receive such an invitation to a more applied workshop. I am a mathematician, but I'm working in applied mathematics. And in the title, you see four methods. The first is the finite element method, and the finite element method is the standard nowadays, the standard solver for partial differential equation, and were used in all simulations that they are presented yesterday and today. And the finite element method has a long history. Usually I ask how long. I come back to this. Isogeometric analysis is a relatively new technique in comparison to the finite element technique. Namely, it was introduced by Tom Hughes in 2005. The finite element method, it depends on, if you ask an engineer, we say in 1955. If you ask the mathematician, depends. It was current in 1943, yes. But it has a longer history of 150 years. 150 years, indeed. It was a Berlin mathematician who used this triangular meshes and piecewise linear elements for the proof of existence of a partial differential equation. And when space-time, usually you solve a time-dependent problem by time-stepping methods, but as explicit Euler, implicit Euler. But here I will use a completely other technique and also relative new techniques. And we need adaptivity. Of course, adaptivity is now also very standard in the finite element method, but I use it also in a space-time setting. Well, of course, the results which I am going to present are done in a collaboration with many people. So here you see a picture gallery of all the contributors. I want to mention Sergei Repin, well known for his functional error, a posteriori error estimates. So I will discuss also this. Freddy Drölsch, who is well known in the optimal control community, and he wrote a famous book. Olaf Steinbach from Graz, so with whom I also have a long cooperation, and the other people were working as postdocs or PhD students in my group. For instance, Christoph Hofer, who is now working with the RISC company. There is an outline of my talk. After an introduction, I will go to variational formulation. There's a lot of mathematics here. When I introduce to you this new isogeometric analysis, but for space-time setting. And I'm very sure today, and almost all the commercial codes like Abacus, ANSYS, Nastran, you have a finite element technique, but maybe in 10, 20 years, you will only find the isogeometric analysis there. When I go back to the finite element method in connection with space-time discretization, and finally I come to optimal control, to optimization method, but I will have an intermezzo after the isogeometric analysis, where I go to the shape optimization problems you are interested in. So, okay, half a direction. So I look at a well-known problem, parabolic initial boundary value problem is nothing else than the heat equation. So it models heat conduction or diffusion, where sigma is the heat capacity times the density. Nu is the heat conductivity coefficient. F is the heat source. I use Dirichlet boundary temperature on the boundary and given temperature at the initial time. So we live in a space-time cylinder. Omega is the space domain. 0t is the time interval we are interested. So the middle phase is denoted by sigma, and the side phases, the lateral phases denoted by sigma, and the initial phase of a space-time cylinder by sigma 0, and the final will be denoted later on by sigma t. So this is the heat conduction problem. I am also interested, or our motivation came from eddy current problems. In 2D, this looked like a heat conduction, but at right-hand side, you have an additional term that comes, for instance, from permanent magnets. So F is a vector function. This is the magnetization with voltphase F. This F is impressed current. This is one over this is the permeability. Sigma is for electrical conductivity. I'm interested also in this. So this is a distribution on the right-hand side. So F can have jumps as a function. And if you take the derivative from a jumping function, then it will be something like a delta function, in this case, a line delta function. That is typical. So the usual approach is time-dependent problem. The dynamic problems, if you have two time derivatives, is a time-stepping method. So you use a line functional formulation, and then the vertical method of lines, you discretize first in space. Then you end up with a big system of ODEs, and this is then solved by implicit Euler or explicit Euler or by Runge-Kutta method. You can do it vice versa. First discretize in time, say by implicit Euler. Then you have a sequence of elliptic problems, and then these elliptic problems are solved, say, by the finite element method in space. Or more modern approaches, you have time slices, I say only for words, time discontinuous Galerking or discontinuous Petrov Galerking. But all these methods from time slices are close to 1 and 2, namely lead to a system. If you write all time levels in one system, when you get such a system, and of course you use it by time stepping. You start with the first time level and then solve a system, get the first solution for temperature on the first time level. The initial time is hidden on the right-hand side. And then you bring this to the right-hand side and solve for the second and so on and so forth. This is time stepping, but this approach is sequential. So if you have a big parallel computer, this is not so nice to do this, of course. So the people were thinking on parallel in time methods, and there's a nice paper by Martin Kanter, an overview over 50 years time parallel methods. So this was in 2015. And there are a lot of papers now on parallel in time methods, for instance, multigrid methods. So here you see some citation, by far not all. So I come to our IGA approach, but I show you the lowest order IGA, and this are finite elements. P is equal to 1. These are tensor product finite elements. So I show only the results. So we construct a multigrid method in space and time, distributing the cores. Cx are the cores in space, Ct are the cores in time. And we solve this problem with 10 billion unknowns and more than 100,000 cores on a Livermore, on the quartz machine, a Livermore in 200 seconds. So this is possible. But in this talk, I do a completely other approach. For me now, T is now just another variable. So I will denote T by xt plus 1. And we are living now in the space-time cylinder. T is just another variable. And I solve, this is a 2D problem in space, I solve in the space-time cylinder, and you see here finite an adaptive finite element mesh of a space-time cylinder, no time slices. And here with moving interface, I come back to this, and this is with isogeometric analysis, a moving domain. A moving in space domain gives you a curved space-time cylinder. So I would hint you to the paper that is in our book, Space-Time Methods, by Steinbach and Young, with a nice overview paper of all these space-time methods. It started already with the time slices, but these time slice methods by Johnson in 1982, and then there were some papers when there were, and then there was a revival of space-time approaches in connection with big parallel machines, of course. And now I can also add a lot of citations. Pros and cons of space-time methods. The pros are you can do a parallelization in space and time, like an elliptic, like in a static problem or stationary problem. Additivity you can do simultaneously in space and time. You saw with mesh. Moving interfaces and domains in space are fixed in time. This is a fixed geometry. There are no movement in space in the space-time cylinder. This is interesting. Optimization problem, usually you need the adjoint problem, and if your problem is forward, your primal problem is forward in time, then the adjoint problem is backward, but in a well-posed sense. And here I mentioned only stochastic PDEs. I will not discuss this. There are cons. Cons is, of course, you need more memory. But you can do parallelization, you can do additivity, and you can reduce the memory requirement. And causality is another point. This depends on what kind of finite element, for instance, you used. If you use discontinuous Galerkin, when you have causality fully. If you use continuous ansatz function, when you have causality up to the discretization error. Pros of IGA over finite element, over the finite element analysis, finite element method. The IGA, the most important idea is you bring together computer-aided design, simulation, optimization in one package. You use one type of basis function for representation of a geometry, for the simulation, for approximation, for solution, and also for handling for optimization. This is one package. And the functions, the basis functions are splines and orbs, for instance. So therefore, we have no geometrical error in technical application. Finite element method, you approximate your geometry usually by the finite element methods. In finite element method, you have a so-called H refinement, mesh, make the mesh finer, P refinement, so higher order polynomials, and R refinement, so you move nodes. And here, in addition, you have a K refinement. You make the ansatz function smoother. You will not do it in the finite element method, but you will do it in the isogeometric analysis, because when you get the best accuracy per degree of freedom, with the highest smooth spline or norms function, eigenvalue problem can be handled in a more appropriate way. Cons, assembling and the solution of a system, the assembling of a system, solution of a system, and the rule implementation is, of course, more complicated. And assembling techniques and solver techniques were a hot topic in the research in the isogeometric analysis. So now come to mathematics, the heart of mathematics, variational formulation. All discretization methods, like the finite element method, isogeometric method, use a Galerkin technique. So we need first the variational formulation, and I do it in space and time. So let me look again at this parabolic equation as a model problem. Here again with the distribution on the right-hand side. When what you do in the variational formulation, you multiply by a test function. In a line variational formulation, the test function depends only on x, but here's the test function depends on x and t. When you multiply the PDE by a test function, and then you use integration by parts. If you do this, then you end up by a variational formulation. I write this like an elliptic problem. I look for a solution, that has the derivatives in X and that fulfills the boundary condition, but not the initial condition. Do the partial integration. The initial condition is a natural condition built in the original formulation. So, and here the test function must be 0. This means on the top of a cylinder with a sigma t. It's a original formulation. So now I show you some results that maybe you do not understand from the notation. But already Olga Ladyshinskaya from St. Petersburg, and I make my PhD in St. Petersburg, show existence and uniqueness and some additional results for these variational formulation. So we have existence and uniqueness, and we know some smoothness in T. So if you take the L2 norm of a function, omega, then it's continuous in T. This is very important. So then there is another result that is very important for us. She shows that if you have no distribution on the right-hand side, and if the coefficient is 1, but smooth is enough, then your partial derivative with respect to T and the Laplace operator is an L2. It's an L2 integrable function. That means this is true. This is a very new result from 2015. That means you can write the PDE in a strong sense. You can write as it is in PDE. In the original formulation, this is not true. So let's assume that now we have this formulation. But now I come to isogeometric analysis, where I will start with this setting where I can make use of the PDE, at least locally. This is called maximal parabolic regularity. It does not mean that you have singular solution. You can have very singular solution in the case of maximal parabolic regularity. But you can write the PDE. So space-time isogeometric analysis. What was the idea of Tom Hughes in 2005, published in 2005 with co-authors? So you can represent your computational domain, so in your case it's a plane, by multi-patches, of course, by mapping a parameter domain to patches. Here I use only one patch for simplicity. So I map my space-time cylinder. My space-time cylinder is imaged by the unit square here. So I map this very easy. But this is the space domain. This can be a complicated car or something. Here's only interval in 1D. I map this to the space-time cylinder with one mapping. And right, and in nodes, and you have a tensor product mesh. And when I define the basis function, that are the splines, I did not draw the splines here. 1D splines, for instance. And then I use the tensor product at ansatz functions. So these are the tensor product ansatz functions then. And then I map this to this space-time cylinder. So it's very easy, the mapping. So then I can define for IGA space as all splines, tensor product splines, or spanned by all tensor product splines from the basis, spanned basis function. So I define the basis function in the parameter domain, have this mapping, and then I have this in the physical domain, and the span of all such functions gives me a space together with a boundary and the initial condition. This is the space where I look for the solution. Okay, for simplicity, I assume that the initial conditions are 0. So what I can do then, again, I assume that I have maximal parabolic regularity at least locally, and every such parent cell K is such a parent element. It's not the same as the final element, only in the case P is equal to 1, in the bilinear function, for instance. And scribe K or calx K is a set of all these elements. So then what I do, so let's assume U is a solution of this, PD, with heat conduction. So with identity. When I multiply this by a test function, but with an upwind, because I look now at time, at the time derivative, as a strong convection in time. And if you have a convection in space, for instance, you should take an upwind function. This is SUBG. SUBG. Streamlined upwind Petrov-Galerkin. So I use this one. Not only a test function VH, but this upwind test function. So when I multiply this, integrate over the parent element, then I use the abbreviation for this integral, this is L2 inner product, and then I omit the L2, so I have the index k with the integral over k. So then I sum up over all elements, and then I do integration by parts, only here, is integration by parts. So the boundary integrals will disappear, are zero. So and this is now my functional form, space-time functional form. I know that the solution U fulfills this for all test function. I have this. Fulfills for all test function. This was trivial derivation from the BDE. Okay, now it's clear. I look for approximate solution. That means this is spanned by all basis function with unknown coefficients, of course, from the space, from this IJ space, such that this functional identity is fulfilled for all test functions. So again, here the bilinear form and the linear form. And if you subtract from this, you get zero, of course. And this is the famous Galerkin orthogonality. And if you have a numerical mathematics Galerkin orthogonality for the discrete bilinear form here, H, then you are on the heaven of the numerical analysis, then you can do everything. And what you can do, first we show playing with upwind parameter, theta k, we can show that this bilinear form is uniformly positive for all test function with respect to this discrete norm. This is the normal energy part of the norm, and we have this upwind part. This is necessary, otherwise you cannot prove this. So if you have this, you can easily show that the solution must be unique. Coercivity means you have a unique solution. And if you're in a finite dimensional case, you can rewrite this discrete scheme as a matrix. It's a big matrix, one big matrix, with all the unknown coefficients that are all coefficients for the complete approximation of a solution in space and time. We solve only one system. So if this is unique, then the matrix is invertible, so you have a unique solution. The matrix is non-symmetric, of course, because you only have one time derivative, but positive definite. Okay. You are, if you have solved the problem, if you have solved this big system, then you have solved the problem. Okay, some more analysis. I will go very fast through this. This is mathematics now. We show also boundedness of a bilinear form on an extended space. This is the star in an extended norm here with a star norm, and we extend the space basically by the solution space. If you have this, then you can easily show a discretization error estimate. We want, as mathematician, we want to be sure that the whole thing converges. I estimate the norm of the error, U minus UH, U is unknown, by the best approximation error in these norms. So then from this, you can usually derive a priori estimate, like it converts like H to some power. But this is an a priori estimate, and this can be not used for computing the error. And engineers interested in the error, after the computation. And I will present to you, and this is very interesting also for a solution that you come by heuristic methods like machine learning, like neuronal networks, for instance. Let us assume I have a solution. I have an approximation coming from a simulation, now UH, a space-time finite element solution, or another finite element solution by time stepping, not so important, or coming from an experiment, from measurements, or coming from neuronal networks. So you have a solution, and now you want to evaluate the error. I use 3 triple norms. This is the first norm with the H is our norm that I had for the a priori estimate. This norm is this one that estimates the gradient of a solution and the approximate solution and the error on the top. And the second one with the delta is an identity. And this was proved by Anyam and Pauli. They proved that this error norm can be computed if you have an approximation. And you have to compute this. This is really a very nice result. But you need a Laplacian here. You need to be in the setting of a maximal parabolic regularity. We are, but maybe also you want only this one, not with a Laplacian. When we have a Majorand, an estimate from above, and we can also provide estimates from below. Estimate from above is called reliability, estimate from below are efficiency. We can do both. And this looks like this. So you have an approximation. We are back to our UH. V is UH. It's here and here. And then you have to provide a flux. So, okay, you can take gradient UH when this is 0 and then you have an upper bound. But better is to minimize this Majorand by solving this minimization problem. And this minimization problem, again, this Majorand, can be solved as follows. You solve a diff problem here in the space-time cylinder when you get a very good flux here. You get a very good flux that gives you a very good bound of a Majorand. I come now. So how do you compute this? So you use IGA for your solution UH, as I explained, with our matrix. So we measure the time you need for assembling and solving. I will not go to this. When you do the same with a flux, you compute the flux with a vector function now, or vector function, yes. And you compute the coefficients or the control points in IGA by the system, with the system matrix coming from the minimization problem. Okay. So then it is additional work, of course. And now you can benefit from an idea that was published by Kleis and Thomas from my group at the time. So you solve this on the IGE space SPH. This is on the grid H, this one grid, with polynomial with splines of a degree P of a highest smoothness P minus 1, always highest smoothness. And when you solve for the fluxes with a higher degree of the polynomials and higher smoothness, but on a coarser grid. So this is very efficient. So there is a second Majorand that I will not explain. I explain only this one. So you solve this here and the flux here. UH, the temperature say here, and the flux here, and so on. So this is the additive algorithm. You go with you start with a grid, and then you refine using refinement to the Majorands. So I show you some examples. So this is a smooth one. This is a smooth example with a high oscillatory example, and we see this refinement process. You see also with a uniform refinement. You see here the full rate. The full rate is h to the power of p. This is this one. Always with the expected range due to the estimates, and you go even better with adaptivity. So efficiency in the indices for the second example with a high oscillating solution. This is not so easy, a high oscillating solution. And we do local refinement. And with this high oscillating solution, we would like to measure the quality. Here I know the solution, so I know the error. And then I have this part. In general, I have only this part. And here if I compare, the best thing is 1, as in for identity. But here I always have between 1 and 5.7, something like this. This means very good upper bounds. And here you have a convergence rate. The time, I have no time to discuss. You see here the grids. So again, convergence order. So we have other example. Here's an example from a paper from Devaux and Schwab, where we have a singularity in the beginning. If you take the derivative here in time, you have t minus 1/4, so you have a singularity. And here you have a singularity in the third derivatives. And I use p is equal to 2, so I would need good third derivative, but the additive procedure produces not only the reduced rate, this would be the reduced rate, produces the full rate. So these are the grids. So this is the bad singularity, and this is the singularity in a higher order, so you find this. Here's another example where you have a time singularity in the mid of the time interval. And here I choose it in such a way that we have no, but I have no time to explain, there's no maximal parabolic regularity. Here we have an elliptic mesh. So now I have an intermezzo of say 5 minutes. Optimization, IGA simulation optimization of electrical motors. So you see, of course, the rotor is a circle. If you have the cross section is a circle, so you can represent the circle by NURBS in an exact way without geometrical errors. So of course, usually you compute a quarter of the cross section, but I will show you the full cross section. And here I have an optimization problem to optimize the run-out performance. So this is the cost functional. Gamma is the middle line in the air gap. So this is the air gap here. This is the air gap. So and this is a given sine function subject of a 2D magnetostatic problem. So here I have a linear problem for simplicity. And what you then do, we compute the shape derivative via the adjoint problem. The adjoint problem gives you the sensitivities. So with the same problem here, because symmetric, but with a special right-hand side coming from the derivatives of a objective. So when we project the shape derivative by a elliptic and symmetric bilinear form, in order to compute this with a vector function t, this is nothing else than the displacement of a shape. So here I want only to change this part. These are the electrical magnets, these are the coils. I will only change this part, ferromagnetic material. So this can do, this we can do. So this is the algorithm, compute the solution, compute the adjoint, compute the displacement. And then you can proceed. And then we decompose these electric machines in 72 conforming patches. So this is the solution without coils, so only permanent magnets for splines that are based on polynomials of a degree 3. This is for continuous Galerkin. So I have CG and DG, continuous and discontinuous Galerkin. So this is a fast method for solving the corresponding problems. This is called isogeometric tearing and interconnecting method. This is a method that is a domain decomposition method that was constructed for solution of parallel machines. And here you say we solve a problem with 3.5 million unknowns on 128 with 128 cores on the parallel machine with 1.5 seconds. So you can find this in Christopher, similar description of this method in Christophor's thesis. This is the result of an optimization process. So this is a distribution now of a ferromagnetic material. Now this is air. And we could halve the objective function. So of course, a machine is rotating. So we want to have this for rotating machines for something like this. Then we use here discontinuous Galerkin with non-matched patches. This is working. So here I have a solution. This must be the same solution as we saw. Indeed, this is the same solution. And they should rotate. If you see this, then the method is working. So this is work in progress. And now back to space-time. So I cannot go through the finite element analysis of the space-time methods. So you have an electrical machine. So this is a cross-section. This is rotating, as I show. You can do it. Or you can look to this rotating electrical machine from a space-time point of view in a space-time cylinder. This is not the 3D machine. This is space-time cylinder. And then this rotating electrical machine is fixed, a fixed geometry in a space-time cylinder, and this can be used. So I have no time to discuss now this from the finite element method. This is similar to the isogeometric analysis. So you are interested in optimization. I will go to the next, to the optimization thing. So we have a lot of, I show you this is interesting. We have a moving source, and this is used in additive manufacturing. Maybe this is interest for you. We use DHB splines for the refinement, as always here. And this is a source that is moving. And I want to compute the temperature field. After the computation, temperature field looks like this. So this is a moving thing, but this is space-time. We did this in space-time, and again, we use additivity here, and we can always restore the full rate, namely h to the power of p. H in terms of unknowns. Of course, we do not know the solution, so we have a reference solution on a verifying grid here. So these are cuts through the space-time cylinder. So when a cut can look like this is on the top, this is on the initial, so this is fine. If you cut tetrahedral mesh, the mesh is fine. It's shaped regular when you get something like this. So here you see the efficiency, and we see always the functional are near to 1, the residual are not so fine. So we use also residual here. So this is another example. I go through this. So now I come to my last part. This is optimal control problems. So optimal control problems are always can be always formulated as follows. So similar to shape optimization problem, you have a cost functional objective. Y is the state. So the state solves the heat conduction problem, and the control is the heat source, U. So, and when you prescribe a profile, you want a profile, and you want to approximate the profile, the desired state, UD, in such a way, by U is unknown, you won't find it, but it's very close. This is the Hilbert problem. You need always a regularization. It can be also interpreted as cost for the control. You need always this. Okay. This is a space-time tracking optimal control problem. This is called L2. This is L2 norm, L2 regularization. But I can also use a combination of L2 and L1. This is the so-called sparse regularization proposed by Stadler in 2009. The same state equation. Or what we proposed in a recent work, regularization by a negative norm, H-1 norm, by a distributional. We allow distributional controls. You will see what this means. So this is the optimality system. So you know a function. If you want the minimum of a function, you take the gradient, and this must be 0. You do here basically the same with the solution operator. This is the optimality system. So you should solve this. And then in L2, you have really P plus lambda U is equal to 0. You can do it when you have 1 over lambda. Here in the H minus 1, in the so-called energy regularization, is more complicated. We have to solve a Laplace problem here with right-hand side U. And then we can eliminate this. The original formulation looks like this. If I subtract the second from the first, then I can write with a big bilinear form. So now I jump about the theory. This means we can prove existence and uniqueness. We can prove error estimates of error by the best approximation. This is everything is here settled in the mathematics. And we can find such a priori elements and also a posteriori things. Two examples. The first one is in space 2D, I have a circle. I want to approximate my desired state as this. This is a circle that starts to expand from 0 and then shrink. In the space-time cylinder, this is a ball. And you want to find a control that gives you this profile. So, of course, you use additive method, additive finite element method, and then you produce, these are cuts, here you see the times, and here you see the space-time cylinder. This is 2D in space, 3D in space and time, and this is a ball. So you have a space-time mesh. If you cut, you see this. Okay, here are the results. This is the different T's. This is the desired temperature, what I want. So this is expanding and shrinking circle. This is what we compute with a little bit diffusion here. And this is the adjoint. This is sensitivity. And this is a control. And the control is sitting on the circle. It's a line, it's almost a line delta function. In fact, it would be a line delta function. So this is a control. By the way, it is made for electrical machines. You can technically you can realize this very easily. So now pictures. This is the state. This is not you. You is another notation for another community. This is the state. So you have here by the energy control a very nice reproduction of the state, and this is a control that is very different from the L2 control, from the sparse control. Sparse control is better, of course, than the L2, but here we have a perfect. Okay. Now the last example is a nonlinear problem. So we have I use L2 control for simplicity, L2 regularization for simplicity. But the state equation is nonlinear. We have a nonlinear term of a type y to the power of t. This is a product of this. This is not so easy. You can generate very interesting solutions. This is a so-called Schlögl model, and this is a simplification of a Fitzhugh-Nagumo model that plays an important role in chemistry, but also in medicine. So, and we add box constraints for the control. The control function should lay between two constants A and P. So then the optimality system looks like this. Here we realize the projection of the control to this interval. So you have to solve this. We were able to construct an exact solution for special. We are very proud on this exact solution. And here you see the state. This is a turning wave. It's almost the desired state, a turning wave. The adjoint state with the sensitivities and the control that goes with this. Okay. These are the meshes in the space-time cylinder. This is 3D. We use tetrahedral elements and additive mesh refinement. These are again the pictures I do all for the meshes with the solution. So this is the reduction of an objective. And up to 4 million unknowns. We use fast solvers, and this can be computed on a PC or laptop. We have 3 publications on this in very good journals here. You can find the results from this year, very new results. Conclusion: we have discussed unstructured additive space-time, more isogeometric analysis than finite element analysis for solving linear and, as you saw, nonlinear parabolic evolution problems as constraint for optimal control problems without and with time upwind stabilization, leading to discretization error estimates in different norms. With stabilization, we have stronger norms. This is the point. Unstructured space-time methods have agreed potential with respect to additivity, space-time additivity, parallelization, space-time parallelization in simultaneously. You can easily treat moving interface in domains because in the time space-time cylinder they are fixed. Optimal control problems are specially suited for optimal control problems, the so-called KKT systems, because the state is forward in time, the adjoint is always backward, but well both backward in time. Shape optimization can be treated. Future challenging research topics also for young people, at least working in but not only working in mathematics, reliable and efficient a posteriori basis for adaptive procedures. I want the proof conversions and optimality. I see this in my numerical results, but I want to prove this. We want robust solvers, parallel solvers. So we use, for instance, here fast AMG or Emily solvers. And for instance, my PhD student was in Liverpool working together with Wasilewski in the labs, and they solve a problem with 1 billion unknown on 4,090 cores on this machine, this quartz, in 3 seconds. So shape optimization, or have 2 times optimization based on space-time simulation. This would be interesting. So we are working on this. So thank you very much for your Zoom attention.
Thank you very much, Professor Lange, for presenting your very nice work.